my water stays as a liquid, even though that the water molecules are pushing outward, right? Atmospheric pressure is the reason why they stay as a liquid, because they are pushing back down on them, right? Right? So atmospheric pressure you can also see as air pressure or barometric pressure. Okay, those are the other names for air pressure. Okay, and yes, you do need to know all three names. Okay, they are interchangeable, but they all mean the same thing. They all mean that it's the pressure due to the weight of the atmosphere pushing down. Okay, so how do we measure them? All right, well, this usually measured by a barometer. Okay, hence why it's called barometric pressure, because it's named after the device that we use, known as a barometer. Okay, now you can have a mercury barometer, which they used to have in all of the labs. They don't have them there anymore because mercury is one of those things, or at least liquid mercury, which is mercury at room temperature, has basically been outlawed being used in tools. Okay, and then you have an aneroid barometer. Okay, this is a mercury barometer, or in some cases they use it as with water, but in this case we're using it with mercury. So this liquid here is going to be liquid mercury, which is the phase that mercury is at room temperature, or STP, standard temperature and pressure. Okay, this is 760 millimeters of mercury, and you're going to see mercury, its chemical symbol is capital H, lowercase g, and I would highly recommend you write that down. Mercury is capital H, lowercase g. Okay, that's its chemical symbol. That's the one you're going to see on the periodic table. So if you see MM, capital H, lowercase g, they're talking about millimeters of mercury.
Wait, what is mercury again?
Capital H, lowercase g. Okay, so what ends up happening is, with the barometer, the more atmospheric pressure that happens, go back, okay, it pushes down the mercury, putting it up into the tube, and it actually gives you, okay, what the reading is. The one on the left is an aneroid, okay? Yep, and you have to know that they are both used to measure pressure. Let's see if this wants to work. Don't you love when things work? Oh, here we go. I just love when things actually work. Here's a little history.
Grammarly does more than catch errors. With Grammarly, you can find... Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist, because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
All right, so that's pretty much how we ended up with the barometer, okay? So I just named something before, and I said STP. STP stands for standard temperature and pressure. Everything that you see here, okay, is considered to be a standard. When you do an experiment in a lab, you're under the assumption that you're at standard temperature and pressure. Because room temperature in this lab versus room temperature in the lab downstairs, like think of it this way. Your temperature right now up here is a different temperature. You guys have all gone down to the earth science lab before, and it feels freezing down there, but it's nice and toasty warm up here. So when you do labs in general, or research components, you need what's known as standard pressure. Now, these values that I give you are all equal to each other. They just have different units. So 1 atmosphere, or 1 ATM, is equal to 760 torr, which is equal to 760 millimeters of mercury. Okay, these are all standard pressure values, which are equal to 101.3 kPa, or kilopascals, which is equal to 1013.2 millibars, which is equal to 29.92 inches of mercury. I believe that's the last one. Nope, one more, which is equal to 14.7 pounds per inches squared. All of these values you need to know. They are not on your reference table. They are all standard pressure values. Okay? And if you all look on your phones at the weather app, right? You all look there. Down at the bottom, it says 30.1 inches of mercury. What that tells me is currently in Fresh Meadows, I mean, I know you guys aren't all here, but in Fresh Meadows, we have higher than standard pressure. Okay? Now, I want you to keep an eye on that. For those of you who are like me that get pressure headaches, those are the ones that feel like somebody's pushing down on your eye sockets. Okay? Anytime you get one of those headaches, look at your app. When you look at your app, I want you to notice, is it when it's a high pressure or a low pressure? 29.92 inches of mercury is standard or normal, quote unquote, pressure. Okay, right now it's 30.1 and I have a slight headache, which means that I get pressure headaches when the pressure is higher than normal. Okay, so these values you need to know, and you need to know that they're all equal to each other. They just have different units. That's the only difference. Jared, you good? Okay. You sure? Okay. All right, so this is on your reference table. Everybody look. They got your reference tables. Okay? It's on the same page as the temperature value. So I think it's page 14. And it is. You don't have it go. You're not saved on your iPad, right? Right? So in this case, right, you're not going to be asked to calculate to go from millibars to inches of mercury or inches of mercury to millibars. No. There it is. It's 13. Okay? On page 13, all the way to the right, okay, it has millibars and pressure in general. Okay? So just like I said to you guys, you don't have to know for this class how to calculate from degrees Fahrenheit to degrees Celsius to Kelvin. You don't need to know how to go from millibars to inches. However, okay, on the millibar side, each one of these lines is worth 1, right? But on the inches of mercury side, each one of them is worth 0.01, which is something that you're going to want to write in your notes, okay, so that you don't forget it. Because remember, you have to know what each one of the lines is worth, okay, to go from one to the other. Okay, so let's talk about the factors that are going to affect.
Can you go back to the inches one? Thank you.
No, just write down 0.01 versus 1. Yeah, simple. You don't have to, it's all in the reference table. So in millibars, each one of the lines is worth 1. In inches of mercury, it's worth 0.01. All right, so the factors that are affecting air pressure. The first one is temperature. Temperature and pressure have an inverse relationship. Okay, that means if one increases, the other decreases. Well, how? Well, if we increase the temperature, right, it means that the molecules are going to move more. When the molecules move more, the air is going to expand away from each other. When they expand away from each other, it means that their density decreases. When their density decreases, their pressure will also decrease. Okay? So you have to remember back to what's happening on a molecular level. What is happening to the molecules themselves? Okay? So if you change the temperature, the inverse is going to happen to the pressure. So if you increase the temperature, the pressure is going to decrease. If you decrease the temperature, the pressure is going to increase. All right. Now, this what I just wrote here is exactly the same thing that we were talking about on why hot air rises, right? In the molecular level, the molecules are going to move further away from each other because they are moving more, and those intermolecular forces of attraction are going to come less into play, right? Which means that the further away they are, the less dense they are, and therefore the pressure is going to decrease, okay? Now, the second factor is going to be the humidity or the moisture content in the air. I got rid of my eraser. Okay. Now, guys at home, can you see the board that I'm writing
Yes.
on?
Yes.
Okay. So, I'm going to prove it to you. Water is made up of 2 hydrogens and 1 oxygen, right? Let's break it down to each individual atom. According to this chemical formula here, I have 2 hydrogens and 1 oxygen. That's where I'm getting these numbers. I'm going to tell you, according to the periodic table, the mass of hydrogen is approximately 1, and the mass of oxygen is approximately 16. When I multiply that through, I get what's known as 18 grams for every 1 mole. Don't worry about the units right now, but it's about 18 grams. It has a mass of about 18 grams.
Can you turn the camera, please? It's cut off.
Which way? This way?
Yes, that's perfect. Thank you.
Let me see if my water bottle can hold it there. It is not letting me do. Here, how about that? Is that better?
Yes.
Okay. All right. Versus, we know that nitrogen is the, what is these verses? Is what makes up most of our air. So nitrogen, according to N2, there's 2 of them, each with a mass of 14. So that's going to be 14 grams per mole. Right? And oxygen, there's going to be, I can do math, I swear, 28. There's 2 of them. This is really hard to do while holding this. 32 grams per mole. Okay? I'm just going to hold it like this. Can you guys see that?
No. Not really.
Yeah, I can't see the left side.
So, for nitrogen, okay, there's 2 of them. Each of them has a mass of 14. So 2 times 14 is 28 grams per mole, which is bigger than 18. Right? So nitrogen in its elemental form weighs more than water. Okay? Same thing with oxygen. Oxygen in its elemental form, it's diatomic, which is why it's O2. There's 2 of them. Each individual oxygen weighs a mass of 16 grams, which tells me that it's a total of 32 grams per mole for every 1 elemental oxygen. Okay? Nitrogen and oxygen have a bigger mass than water, which is why if you increase the amount of water vapor, okay, just according to these numbers, right? I'm trying to just make sure you guys can see them. Can you see them, guys? Yes, no, maybe? Okay. Well, if you,
No.
okay. Well, this is the best that I can do. So
Can you put back?
that's the best I can do because it doesn't want to stay.
Yeah, that's good.
Yeah, that's fine.
Okay, so if you increase the amount of water vapor that is now in the normal nitrogen and oxygen air that's around you, that means it's going to be less dense, right? Which means that you're also going to lower the pressure. This tells me that the humidity moisture content has an inverse relationship with pressure as well. So if you increase the amount of water that is in the air, the lower the density will be, the lower the pressure you will have. So they have an inverse relationship. Okay. The third one is the altitude. Right? If you increase the altitude, you know that the temperature is going to also change. Okay? But the density and the pressure are going to decrease. And if you forget, you have a reference table for this. Okay? On the reference table, it has to do with the atmosphere, this one. Right? You have that pressure right here. Right? You have that pressure one, and you can see as you increase in altitude, right, the pressure is going to decrease. Right? So all I'm doing is looking at it from the perspective of your reference table. Right? All right, so your homework for tonight is practice problems on review book page 130, questions 8 through 17. So it's the next group of questions. Okay? I'm going to post this in a few minutes.
Do you want us to submit it?
No, it's the same thing as every other homework. Okay? We're going to go over it tomorrow in class. Okay?